And I don't think we're muted today, so we're just going to jump right into it. Welcome, everybody, to the Bungalows for Bachelors Late Night Learning. Today, we're going to learn about why size matters. Despite all the lies, it actually does matter. So, this is the Bungalows for Bachelors channel where we learn about cool stuff, where I explain how to do things with your house, and you can learn things about your house. And if you want to check out more free stuff, I've got tons of stuff on the YouTube channel as well. Excuse the cough. Lots of free content there. And if you want to join our free school community server thing, where you can chat with us, do community forum stuff, and like share your projects, do all kinds of cool stuff, ask questions, you name it, get involved. Link is in the description below. Check it out. Join it. It's free. It's a good time. You should join us. As well, you should also look into learning about cryptocurrency. It is a thing of the future. It is coming. It is here. Things are going up now. That's nice. Wow, excuse me again. So, specifically, you should check into Hex. There's a this is going to be a problem, isn't it? There's a link in the description below to learn a little bit about Hex. It's basically the world's first blockchain certificate of deposit. So, if you don't know what that is, you'll lock your money up, you get a return on it, take your money out at the end, and you've got more money. Check it out. If you want to be decentralized and not have to deal with other banks and people holding your money, cryptocurrency is a thing you should look into. So that said, let's get right into the content here. So I said size matters. Well, I ought to clarify what that means. So I'm specifically referring to the size of ceiling joists and rafters. Man, recovering from this sickness still. Maybe it was the Rona. I don't think I'm supposed to say that on YouTube. Oops. So, rough start. What is a ceiling joist versus what is a rafter? Well, they are good to know the difference between because they are two different things. We're always referring to two different things. A ceiling joist is generally going to refer to, this is your house cross section and this is your roof. The ceiling joist is generally going to refer to the parts that make your ceiling. They generally are flat. Sometimes, though, if you have a vaulted ceiling inside your house, the ceiling joists can be pitched. If they are your roof, they are your rafter, right? So there's a piece of wood that goes across your room. That's your ceiling joist. And there's a piece of wood that goes up into the attic. That's a rafter. That's a rafter on that side, and there's a rafter on that side, okay? So they're two different pieces of wood. You can also, like I just said, you can have that vaulted ceiling where your ceiling joists are pitched and you actually have two sets of things. And yeah, they're both like doing this angle thing, right? That's the thing, right? If you want a vaulted ceiling inside your house, sometimes that's what you got. Sometimes you don't even have that. Sometimes your vaulted ceiling is just your rafters, right? So that's a scenario that can be done, but that's the difference. Ceiling joists versus rafters. All right. So size matters. Wow. Because, drink my water. If you're going to have a big 24-foot spanned room, you can't just pick any ceiling joist. You got to pick based off of, the room, how far it's spanning. Because if you use something that's too small, your ceiling is going to sag in the future. It's going to be a problem. The same is true of your roof, right? So we don't want our houses falling in and we don't want them sagging. So we got to use the right sizes. Now, where on earth are we going to find out the right sizes? Well, there's some super easy little tables that somebody kindly threw into the International Residential Code that tell you ceiling joists are in R802.5.1 parentheses 1 and rafters are in R802.4.1 parentheses 1, right? Those are the tables that are generally, like there's parentheses here because these are just the first tables. There's a bunch of different tables to select from, and we are going to tell you why and which ones you pick from, okay? So that's where you can find them. And basically, it's super easy because it's literally, you make some selections about the type of thing you're going to build with, and then you just pick the number. Like it's super, you don't need to do any math. You don't need to do any calculations. There's no engineering involved here. It's what is the table? What is the distance between my supports? Done, okay? Now, For most of this, we're going to talk about rafters because rafters are a little bit more complicated, and ceiling joists have the same application, but they're generally flat, so it just doesn't matter. Okay, so your ceiling joists, again, they go from wall to wall, and basically what this table is going to say is, you're looking at this interior span here. Excuse me, inside wall to wall. So the walls have thickness, right? Oops. So technically, you're looking at the inside wall. This number is the span, which is the unsupported length of the of the member. Okay, unsupported meaning it's not supported by the wall. So you can have a 10-inch thick wall. The span part starts at the end of your wall where you've got the clear opening below it. All right, so that's what you're trying to figure out, and that's just for ceiling joists. Rafters are the same, but they're pitched. And a big point I'm going to try to make this evening is that we do not care what the unsupported length is across the rafter itself. We only care about the projected unsupported length from the sky. Here's what I mean when I say that. Okay, here's my wall, here's my rafter, and let's say there's some other wall up here. Okay, and it's pitched because it's a rafter. All right, I don't care what this distance is along the rafter. I don't care. What I care about is the distance between these two walls horizontally, as if I'm looking top down, plan view, right? There's some imaginary line that I'm going to see of this wall and this wall looking down from the sky. That's the distance that I care about. Makes it super easy when you're just reading the plans to like find spans and stuff because you don't really care about the pitches. The pitch doesn't matter, and I'll explain that at the end. I'll explain why at the end. So when you get into using these tables, one of the first things you're going to see is that there's a lot of options for these tables, right? So here's some of the categories here. So first of all, it's going to say at the top, like there's going to be some live load or some dead load. Well, it's going to presume a dead load, generally speaking, but it's going to have some varying live load. It's like, well, what is a live load? And I'm going to refer to roofs from this point on, but ceilings are pretty generic. It's either 5 pounds per square foot of dead load, 10 pounds per square foot of live load for a regular attic ceiling, or if you're going to have storage and it's 10 pounds per square foot dead load, 20 pounds per square foot live load. It's pretty clean cut. You can boost those numbers up if you want to put more weight and stuff in the ceiling, but that's pretty much it. Rafters are a little trickier. So dead load, first of all, when you want to know the dead load, well, what is the dead load? What is the live load? Well, the dead load is the literal dead weight of the stuff you're building, right? When we build houses, the houses actually weigh something. When you build structures, the weight of the material is going to matter somewhat in the design of what you're building because that load's always going to be there. If I build this super heavy like stone roof on top of my house, something's going to hold up the stone, right? So that's a problematic thing that we got to keep in mind. So that's why dead weights matter. And live loads are basically temporary loads. They're either snow load, wind load, earthquake load, or presumed like gravity loads as well, like furniture, a piano, people's body weight, like, your grandpa who's fat in a wheelchair and weighs 600 pounds, like, that moves through the room. That's a live load. So basically what that means is like the load can come and go. It can shift places. It can be over here. It can be over there. We don't know where. And basically they just do a bunch of numbers to figure out average what we should design for in live loads. And that's why when you have college parties on the second floor of a house and you get, 50 students or whatever jumping up and down on a floor system, that's not a live load that anyone in the world uses numbers to design with, because if we did, you couldn't afford to build the house because it would get stronger and stronger and stronger and bigger until you can't afford to build it. So that's why we have to like have a balanced number somewhere. So that's the live load. It's got to make sense. Generally speaking, for a roof, if you don't know what you're doing and you're not in an area that gets snow, generally 20 pounds per square foot live load is going to be the thing. And that 20 matters because that's going to be the thing at the top of the table. The first ones, just assume live load. All of the other tables assume snow load. So if you have a non-snow area, your roof loads are generally going to be 10 pounds per square foot dead load, because that's just what it's generally weighs, unless you have like a slate roof or a tile roof, right? Those numbers are going to go up. You got to be aware of that. But if you have a regular asphalt shingle roof or a metal roof, it doesn't really matter. So ignore the dead load part. The live load part is at the top of that table. It's going to say, hey, this whole table is assuming that you have a 20 pounds per square foot live load. Or, hey, you're in an area that gets snow and your snow load is 40 pounds per square foot or 70 pounds per square foot, right? How do I know what the snow load is? Well, you Google your location and snow load, and it will probably bring up a table from your county or city or something that says, hey, here's the design criteria for this area. And boom, diada, now you know the snow load. So you're going to find out what that is, and then you're going to use that to select like the table, right? Now, there's one other thing to differentiate between table to table, and that's going to be that ceiling is either attached to your rafters or it is not attached to your rafters. What does that possibly mean? Well, here's what it means. If you build a house and you build a regular house with your ceiling doing this and your rafters doing this, right? Here's what's happening. This is your attic. There's no finished surfaces on the underside of these rafters. Your drywall is down here on your ceiling where you see it, right? It's a flat ceiling. You look up and I see, oh, that ceiling is flat. Therefore, my drywall must be attached to my ceiling joists, okay? And then in the outside of your house, everybody can see your roof, right? So we take our nice, pretty shingle materials and we make them look nice. Oh, what a nice roof. Oh, very, very nice. That's the outside of the roof. But on the top side of the ceiling joist and the bottom side of these rafters, there's no material there. There's no finish. It's just wood and it's just cavities and stuff. You'll have insulation floating around here, or you spray foamed up in your rafters and it'll be in here, right? But that's all you're going to see. You're not going to see any drywall or anything. And that matters because the other factor in getting these spans is deflection rules. So generally speaking, these deflection rules exist because people are trying to build houses that don't have cracking problems. If you build a wood wall or wood membrane, whatever, that bends too much and you try to put sheetrock on it and like it bends too much, it's going to shred your sheetrock. It's going to crack it. It's going to do bad stuff. And we don't want to see that. So we come up with general rules that limit that. So the code says, generally speaking, if you have a member that bends less than L over 240, I'll explain what that means in a second. If it is at the L over 240 limit, then generally your sheetrock's probably not going to do a lot of cracking. If you're at the L over 180 limit, it might. And so we're not going to recommend to people that they have the L over 180 limit for brittle materials or sheetrock going on a wall. So what does that mean to me? Well, it means that if I'm designing, I'm trying to select the size of this rafter. That's the whole point here. I just want to know what size the rafter is supposed to be, guys. Okay. So what's happening is you're selecting this based on the idea that like when weight is applied to this roof, it's going to pick a different color. It's going to bow the rafter in, right? In an imaginary world, an exaggerated world, it's going to bow the rafter in like that, right? So if there's some finished material on that surface, then we don't want it to bow as much, aka we want it to be stiffer, aka we choose L over 240. But if it's an attic and there's nothing on there, I don't really care. No one's going to notice this L over 180 deflection thing happening from the outside of the house. It's going to look flat. So that's why that matters. Now, what is the whole L over 180 thing and L over 240 thing? Basically, it means L for length divided by 180 is this total amount of deflection that happens in the center of the object. So if I have an object separated by two walls and I push down on it, then if I have something that's designed for a particular set of weight combinations and a span and species and whatnot, and I want to hit the L over 180, L over 180 number, right? Again, most of these tables, these are designing for stiffness. Ceilings and rafters aren't going to break and fall in and kill anybody. Generally, it's because we don't want them bending too much, all right? In terms of like flexiness. So keep that in mind. That's why these tables are set by these limits. So if I have some amount of deflection, it's going to bow like this. And then in the center, that maximum imaginary distance from between a straight line and the bowed line in the center, that difference divided by the length between the walls. That's the number we're trying to get. So if these walls are 180 inches apart, and we selected this thing based on the L over 180 rule, then that means this will deflect 1 inch. That's just what that means. It's L 1 over 180, L over 180, right? So that's what that means. It's defining stiffness. If you have L over big number, it means very, very stiff, very stiff. So sometimes for exterior walls with like brick on them, or if you have stucco or very brittle things that like to crack and break, you're gonna have really stiff walls. You're gonna have L over 600 zone. Okay. So that is why that matters. So ceiling attached to rafters. So you got to answer that question, right? So you figured out your live load. Let's say it's 20. Cool. That picks out some of the tables. Now there's 2 tables that say 20 live load. Which one do I use? Well, one says the ceiling is attached to your rafters. The other one says the ceiling is not attached to your rafters. Okay. So is the ceiling attached to my rafters? The only time it's going to be that way is if you have a vaulted ceiling where that sheetrock is being attached to the bottom of the same thing that is attached to your roof that like your shingles are on, right? So if you got a big room like this, the big tall vaulted ceiling, and your sheetrock, obviously your shingles are out here, right? If they put your sheetrock on the bottom of these members, then you need to use L over 240. Use a stiffer one. It says literally ceiling is attached to the rafters. Okay, that's what that means. So that said, you figured that out. Now you can select down to one table. Well, now you're in one table. Well, what do I have to know about the table? Well, I'm going to go back to a caveat on the roof live load thing afterwards. But for now, we're going to talk about the like stuff in the table. So first column on the far left is the rafter spacing. That's pretty straightforward. Let's say top down, right, on a house. You're either going to, your rafters are by definition repetitive members, right? You're just going to install a bunch of them that are the same because that's how we build here in America, is we have the repetitive small units that make the whole system of the house. Okay, so if I'm going to space them, well, I need to know how far apart to space them because there's different numbers. Typically, you're just going to do 24 inches on center. 24 inches apart is what that means. Center to center is 24 inches. Okay. There are 4 options in the tables. You can either do them 12 inches apart, you can do 19.2 inches apart, you can do 16 inches apart, or you can do 24 inches apart. You're just going to pick the section of the spacing that you want. And generally speaking, if you're using rafters, you can do 24 on center, simply because most of the time you're going to use 2x6 rafters, 24 inches on center, and like everything else is just going to be bracing. And we'll get to that. But basically, like if you were to have to select a different size, or you wanted to know how to select a different size, because sometimes that's not the cheapest solution. Sometimes the cheapest solution is to like, oh, I need to bump up the rafter size on my whole house to 2x8s, and then I need way less bracing. It's just like super simple. Or I have this one vaulted ceiling where I have this span and I can't possibly put anything in the middle. So I just need the rafters to span 20 feet horizontally, right? So I have to change either the size or the spacing or both. So you got to know the spacing, all right? You're going to pick that out. And then after the spacing, you're going to want to know generally what lumber you're going to use. Now, depending on where you are in the country, you can select different kinds of lumber easier than others. Generally speaking, you're going to be picking from white woods like hem fir, or like the like the Home Depot style, right? It's going to the wood will literally feel lighter because it is lighter. It's less dense. And with density comes less strength, generally speaking. Okay. So you're going to use that, or you're going to use southern pine, which is going to be much more common in the central southern part of the United States, or you're going to be using Douglas fir. Okay. Those are Doug fir and southern pine are like the good, dense, strong, straight, much better lumber. Okay. So if I, and like literally just using stronger lumber allows you to go farther with it. It just kind of makes sense, right? I mean, if you're going to use something that's weak, it's got to be bigger in order to make up for its weakness in order to do that, right? So you're going to pick the species and the grade. So the species, generally speaking, you're just going to pick southern pine if you just don't know, right? And generally, you're just going to be buying grade 2 lumber. Grade 2 lumber is like good standard. This is your lumber you're going to get off the shelf at a Home Depot or at a, lumber yard, right? If you specifically want to work with straighter lumber, you can buy number 1 grade, or you can buy number 1 and better, or you can buy select structural, which have basically just removed so lumber is graded when it comes off the lumber yard, right? As it's coming out, they grade it so that lumber of similar consistencies and strengths and stuff is bundled together, and that allows us to be more specific with design. Allows us for do lots of different things. Lumber that is straighter and more consistent is just more valuable because you have to do less to it out in the field to make it straight and make it work. It's stronger, it's more reliable, it's all these things, right? So if you go the other way, below number 2 is like a number 3 or like a utility grade lumber. That's going to be like all the knots. Those boards are going to be twisty and bendy and all kinds of craziness, just because of the way they're like how they're cut out of the tree. That's just the way the boards are going to end up, right? But they're cheaper. So you want to know the grade. Generally, just pick number 2 if you don't know, because most of the stuff you're going to be buying is number 2. So pick the species, pick the grade, and that's going to get you closer. And then from there, you basically need to just look at like your species and grade. Yeah, you're just going to like pick out the numbers of the table, right? So your the numbers in the table to select from are basically the spans, right? So if I have a Southern Yellow Pine number 2, first of all, I'm in the table of 20 pounds per square foot live load with the ceiling not attached to my rafters, and I'm going to use Southern Pine number 2 grade. It's going to be 24 inches on center, and I need to know, and of course, then you select like the size, okay, right? How far can a 2x4 go? How far can a 2x6 go? How far can a 2x8 go? All the way up to 2x12, right? So you're going to select the size you need based on the room. Generally speaking, you've designed the house design is done. You're not designing your house to like member wood sizes. You just don't. So you have some finished design, meaning I've got a bedroom here and its width this way is 12 feet and its width this way is 14 feet. I should probably put the ceiling joist going across on the shorter dimension. That way I can use smaller lumber and save money. And so you're going to say, well, wall to wall is 12 feet on the inside. And so therefore, let's say it looks like the, ceiling joist can go like 13, 11 or something if it's a 2x6. Well, that's more than 12 feet. So like, I'm cool. Like I can use that. I could go up to 13 foot 11 wide in a room and still have the criteria met and everything. Right. So if I go bigger than that, well, I got to go up a size. I got to go up to 2x8s. Or if I really want to use 2x6s, then I put them closer together. Right. So just use the table, figure all that stuff out. Now, that is for that. Now, there's a little bit of an exception here with these rafters and these tables. There's a thing to keep in mind. Most people aren't quite framing like this nowadays, but in case it comes up, sometimes people like to gain ceiling height without raising wall plate height. And the reason people do that is because you're generally going to be keeping the expenses down on your exterior wall, and you're going to have like a little bit less like air conditioned space, but ultimately you're able to gain the height out of the attic and gain the valuable space out of the inside of this like big roof and wall thing you've built. You're able to convert more of that space into living space. And here's the trick people will do. And you'll see this a lot in like custom homes or, regular spec homes built within the last 10, 20 years. What you'll do is you'll have an exterior wall that's like an 8-foot wall, but you want a 10-foot ceiling on the inside. And your roof is doing this at an angle. Here's the other wall of your room, also an 8-foot wall. Well, in this case, you want a 10-foot wall, let's say. Okay. So what happens is you're going to run your ceiling joist across like this. And of course, you can only have the 10-foot ceiling where your room is capable of going up to 10 feet. Over here, there's a rafter on top of this wall. And so you can't go up to 10 feet. So what you do is you just attach your ceiling straight to the rafter like that, nail it on, and then you typically throw a block in. Where's my marker? You throw a block in right there, make the block go down to the wall too, and nail the block on. And that's typically good enough. All right. So This matters because in the scenario of this, you would have ordinarily looked down at your plan and you would have seen like, oh, my rafter is going from wall to wall, and that must be, let's say, that number is 10 feet. Okay. So if I use, I happen to know that a 2x6 24 on center Southern Pine number 2 is going to go about 11 feet. All right. So if I looked at this wall and I said, oh, if this is a regular situation, then this rafter is going to be 2x6s, 24 inches on center, nothing crazy here. Right. And there's like some support here or whatever for this. That's fine. Okay. So that's that 10-foot horizontal span for that rafter is fine. I don't need anything else. It's good to go. So what happens now, where originally the ceiling joist was sitting on a wall and it was sitting on a wall, but now I raised it up and now this end of the ceiling joist is sitting on every rafter. What does that do? Well, it takes all of the weight of whatever's right here and some of it gets pushed out to the wall and some of it gets loaded over here onto your rafter, right? So now your rafter is doing the work of holding some of this weight, which means that's more work than what it was originally table designed for, right? So what do? Well, there's a table called the rafter span adjustment factor. And basically what it does is it looks at what is this height here that you have raised up into the rafter versus what is the height here to the peak. Like, what is that ratio? Is it 1/3? Is it 1/4? Something like that, right? And it says, well, if it's 1/3, then use 0.6 as your factor. And that means you'll take your allowable span of, let's say, 11 foot for that rafter, multiply it by 0.6, and now your allowable span is like 8 or whatever that number is. So if I load the rafter, now my allowable span is 8 feet for this rafter under this situation, which means I can't, like, I have to support it at 8 feet. I can't go to 11 feet, which means 8 foot's like somewhere over here, right? And there's nothing below this. So in this case, what I would do is I would just put an angled brace down over to my wall, and then everybody would be happy. But I have to know to do that because I've added this extra weight. So that's the adjustment factor. So this is a very technical lesson, by the way. So we've got that going on. Now, one of the things I didn't touch yet was that roof live load selections. Okay. So live load table R301.6. This is a special table because this table is your money saving table. Why do I say that? Well, I say that because if you have a house and you have a big, this is just a one room of your house. This is a great room. And your great room has a vaulted ceiling that slopes down, right? So this is top down view. And there's some beam that's got to go across your room at the top. Everybody's seen that, right? You look up at a big pitched ceiling and there's some beam going down the middle of it. Well, that beam is holding all of this ceiling and it's holding all of the roof on top of the ceiling. Okay. So those beams cost money, and those beams ought to be sized by somebody who understands the math behind the beam, like an engineer, for example. Okay. So how do we figure out the math? That's why this table is so magical, because for someone who doesn't understand how to use the table, for someone who doesn't understand how to do the engineering, you can't use, like, they're just going to say, well, the roof's always 20 pounds per square foot of live load, so we're going to just put that weight on the beam. And you know what that does? That makes your beam bigger, heavier, stronger. And like, who's to say you needed that strength there, right? The whole point of an engineer is to design something exactly strong enough, not to design something over-designed. Anybody can make it over-designed. An engineer is there to use math to say how much do we really need, right? So here's how it works. All right. If you are like basically this is for big beams. This table is designed to like help you with big beams. It doesn't have to do with small stuff. And here's why. If you have a roof pitch, here's like the live load options, right? So this is just a table, man. Yeah, like any other. Okay. So first of all, what is tributary area? Well, this is saying what is the area above this beam like that is loading the beam. That's the tributary area. And I've got classes on how to do that. It's free. It's in my school community server. So if you want to learn about how to get these things, go check out those classes. Framing design program. Go just learn. Go gain your knowledge. So that's a tributary area over the beam. Now, if that just so happens to be like 10 feet by 30 feet, that's a 300 square foot tributary area. Now, what is this chart saying? This chart is using these three columns. What do these three columns mean? Column 1 is 0 to 200 tributary area, which means if you have anywhere from 0 to 200 square feet of area, aka a relatively small member, but like maybe a big beam, you can use these numbers. Next over is 201 to 600 square foot tributary area. What does that mean? That means big beam. Like that's 600 square feet of area of any one designed member is a lot of weight. Like there's a lot of oomph going into designing that dude. Okay. And then you notice on next to that one is the 600 plus. That's just for mat, like huge beams. Okay. Now, what is the trend here? The trend is from left to right. The bigger the member, the less live load you are allowed to use. Why? Because if I have a really, really large thing, that just means, generally speaking, I'm talking about a really big area. And if I'm talking about a really big area, then the factors that go into making a live load, like, are adjusting, right? The whole point of the live load number is to statistically be about relevant for the possible loads the beam's going to be loading. Okay. What kind of live loads do you get on a roof? Well, you get roofers, you get roofing shingles getting stacked, you get maintenance, anybody being up on the roof for any reason, walking around, and then snow is pretty much like the other thing that adds weight to the roof. Okay. So if you have a bigger area, you are statistically less likely to have the whole area taken up by something that weighs something that you're designing for, right? So if I'm going to have 10 guys on a roof and I have a little 10 foot by 10 foot roof, then that means every guy is taking up a certain space of the roof. And I have 10 guys on a roof and I have this huge mansion. Well, I have less weight spread out over the whole roof, don't I? Like there's just less guys unless they're all in one spot jumping, right? So that's why it's all about statistics and analysis of likelihood and probability of weight. So that's what that means. And then on the top to down, roof pitch, right? You're either a flat roof or a 412. 412 meaning 4 inches per 12 inches. 4 inches rise, 12 inches run. This defines the pitch. The higher that number, the steeper the pitch. Okay. So if I have a flat roof to a 412, generally what that's going to mean is that like the flatter the roof is, the more likely you are to like really directly be supporting something. So it's just like there's less room for error basically. So if you go 412 to a 1212 pitch, which is most houses, then you can actually use less tributary area. And then if you go steeper than a 1212, then you're good to go. Now, why on earth would you be allowed to use less weight in your design, which saves you money? That's the whole point here. Why can you use less weight in your design when this roof pitch gets steeper? Well, simply put, let's imagine this. You have 10 people at a party, and these people are like, they're good workers. They like to do cool things. And you're like, hey, everybody, let's get up on the roof and we're going to go fix a pipe that's sticking out of the roof. We're going to go fix it. And they're like, okay, cool. And so everybody goes to get up the ladder, looks at the roof. You know, it's a flat roof. It's one of those cool roofs. Well, that's easy. Everybody's just like, you ever just walking around on the floor. That's not very scary, right? Or maybe it's like a 312 pitch. It's very light. People can walk around comfortably on that 312 pitch and not be too scared, right? But if you have a 1212 pitch, that's a 100% grade, 45-degree angle roof. If you've ever been on one of those roofs and it's any amount of height off the ground, your booty's puckering because like if you've got good grippy shoes, then they're not going to slide off. But otherwise, like, woo, you're likely sliding around. Okay. So they decrease the live load because generally they're saying the steeper this roof is, the less likely people are going to be moving around a moose on top of the roof and adding these live loads, right? So, and that's just typically how it goes. The other thing that's happening is that the steeper it gets, the more dead load you're going to have because you've got more roof. Like your dead load's going to go up because of the pitch factor. But like, so that just means your live load's going to matter less because you're designing more for the dead load than the live load. So that's how that works. Okay. If you want to save some money, you can use the special tables. It's nothing. There's no engineering here. This is just following what the International Residential Code says. And if you follow the code, your house is going to be fine. Okay. So there goes the eraser. Well, let me grab the eraser real quick. I really center that time. So that's how that works. Making progress. Okay. So horizontal load analysis. Here's the last part. Here's your favorite part. We're going to get into a little bit of engineering math here. Okay. So why do we not care about the actual span of a slanted rafter versus the horizontal span of the rafter? Why? Why is that? Well, let's do this math here. All right. If we have a thing spanning 10 feet horizontally and it's got weight on it, right? Everything's got weight on it. That's the whole point. The weight moves down. Gravity acts down only. So what that means is all of the weight above this thing is acting directly perpendicular to the thing that we are like using to support the weight here. So it's going to want to bend down this way. Okay. If we're talking about a wall and the wall is getting blown by the wind, again, walls are vertical. All we've done is we've changed the orientation. The wind blows this way, right? The wall wants to bow in like this. Again, most of the forces are perpendicular to the item that we're doing. This is the worst possible direction. This is going to make it want to bend the most. If, for example, the wind was blowing in such a way that the wind blew kind of like down like this, right? Well, there's a little bit less force on this wall now because of what we're going to basically call vectors, right? Force vectors. You ever here's what a force vector looks like, guys. Force is coming down at an angle. Every vector can be broken apart into two components, really in any direction. But in the useful direction, we care about how much is it blowing in towards the wall. I don't care about how much the wind blows the wall into the ground because the wind's not going to push the house into the ground any harder. Nobody cares about that, right? We care about this one. So here's how that works: is you basically can draw a triangle that makes the two components of this guy, and this is just doing math. Okay, there's some 90-degree angle here, and there's some angle here that will allow us to figure out, hey, if my wind force in this direction was 100, then what is the horizontal component of that 100? I don't care about the vertical component because that's not bending my wall, right? We can apply the same thing to the rafter. It's like, why is this guy talking about wind walls when we're talking about rafters? Here's the rafter. Okay, it's slanted at a 45, let's say, because that makes my math easier. All right, it's supported down here at the bottom, and it's supported up here at the top. Okay, gravity acts down, right? So what happens is, if I were to draw, make it easy for you guys, if I were to draw and break apart the force diagram for this, here's what it would look like. You would get one like this and one like this. All right, I just made a triangle that represents this force just broken apart in two different components. One component of the force is taking the rafter and it's doing this, remember? It's doing the part that's trying to bend the rafter. That's the thing that like makes things crack. That's what we choose our span from, right? And then this part is just kind of like compressing the rafter. And while that does stress the rafter a little bit, that doesn't hardly make a difference in terms of our design. So that's what happens. Now, let me draw you an exaggeration because the 45 is hard to see the difference. It's right in the middle. Okay. So here's an exaggeration. I'm going to draw one flat. Okay. Here's a flat rafter. And I'm going to draw one really steep. Make the point really clear. Okay. That's a super steep rafter, right? Here's what happens. Here's the horizontal span. Let's say that these numbers are even. So this is 10 feet across, and this is 10 feet up the length of this rafter. Okay. This horizontal span is obviously 10 feet, and this horizontal span is some other number. Let's say it's like 2 feet. Okay. Now, gravity's working the same. The board itself is the same length, therefore it's got the same loads. All right. So now gravity's acting on this thing. Its own weight's trying to push it down. All the weight of the roof's trying to push this thing down, right? Weight's going down. Okay. Now, here's the force like breakout. How much force is going down and acting as the perpendicular to this member part trying to bend this? 100% of the weight, because this thing's perpendicular to the ground. Sorry, parallel to the ground, right? So all of this weight is perpendicular to this thing, which means all of it is trying to bend it. What about this one? Let's draw a little arrow, right? And figure out. We've got one arrow coming straight down, and then we've got two arrows that make it up. One arrow goes like this. One arrow goes like this. Now, the beautiful thing about vectors is that the physical size is actually the representation of the proportions of like the components of forces. All right. That was a lot of words. Basically, what it means is how in this triangle, which arrow is bigger and which one is smaller, right? So the smaller arrow is the one that is perpendicular to the member, and it's the one trying to bend the member. Okay. The longer arrow is the one in line with the member, and it's like compressing the member, but we don't really care about that. So in this scenario where I took the same board and like analyzed these are two different horizontal spans. This one with the shorter span is experiencing way less bending, right? And so that's why we simply don't care about the pitch of the thing, because as the pitch goes up, and technically the weight becomes more because now there's more roof, right? So if I were to draw this thing with a 10-foot span, the thing would be like up here, right? It'd be like super long because it's got to like make up for this distance, right? It's got to go up at an angle, right? So that means more weight. So steeper pitch means more weight, but steeper pitch also means that more of that weight is just going into the compression of the member, and less of that weight is trying to actually bend the rafter itself. And that happens to happen at a ratio that just like makes it irrelevant. Okay. So that's why we only care about the horizontal span of the rafter. We don't care about anything else. So don't ask, hey, what is the span? Is it like the horizontal span, or is it the like unsupported length of the thing at an angle? Like, what is it? I used to wonder the same thing. And that's why I am trying to explain this, because I've finally solved the problem, right? So, whew, man, that's that. I hope this has been somewhat informative. And if not, then sucks. I appreciate you watching and spending the time anyway. Thank you guys for hanging out and watching this educational session. If you want to learn more about framing, like this kind of stuff, again, check out that school community. It's free. I got a home design program and a framing design program. You can check it out. And yeah, I appreciate you guys being here. So I will see you on the next one.